Good afternoon, everyone. Um, so yeah, this will be more about cesium dimers, but the reason we uh, okay, the reason why we looked into this dimer is because we were interested in, or still are interested in cesium potassium molecules. So we've been obviously developing the setup and trying to benchmark it, and so along the way we did some work where we, among other things, laser cooled or and magnetically trapped natural abundance 40K, so fermionic potassium from natural abundance source, which is like almost nothing, but we managed to get close to 10 to the 5 atoms in the magnetic trap after sub-Doppler cooling to like 10 microkelvins. And actually, we kind of followed with this and tried to get, we got a mixture of potassium 39 and potassium 40. That's actually probably the first time anyone has created this mixture in the ultra-cold regime. Well, we got only to the magnetic trapping point because it's still, again, natural abundance of potassium 40. So unfortunately, we couldn't really use it for anything super useful. I mean, we did see some interactions, or I guess interspecies losses, which showed up as a decrease of the lifetime of the trapped atoms. So we also did some work already with KCS, so we managed to see Feshbach resonances in potassium 39 with cesium. That's actually something that Christoph has been doing, including his recent results that have been just posted on archive. We did see a little bit more resonances than he did, but we did see the ones that he saw as well. So I guess from my point of view, it's good that there's like an independent benchmark that we are doing things right, or maybe that also Christoph is doing things right. But what it's definitely completely new is Feshbach resonances in potassium 41 with cesium. And these are, turns out that the potentials that are describing this are very off. So pretty much none of the resonances that were predicted are within even 15 Gauss if it comes to our measurements. And so the black ones are in the really the lowest spin states here. So they are also broad. Even the theory predicted only one broad resonance. Here it seems like there's at least 2 in this state and many more. Okay, but so obviously to do anything with molecules, oh, actually, so this work, all the work with KCS has been done by Mateusz and Kuba. These are PhD students about to graduate, and what I will be talking about is has been done by Corey Dincher. He's now developing quantum computers in Germany, ion-based, by the way, not neutral atoms. So, in order for us to do any spectroscopy moving towards ground state molecules of potassium, obviously a sensible step would be to test your laser systems on something that's known, right? So obviously cesium and potassium, it looks like, or looked to us like for cesium, there's this purely long range potential fairly close to the dissociation limit here. It's like a double well potential. And this external well has been extremely well characterized. So we felt like, let's try our laser system over there because everything is known. And that's true. I mean, everything has been measured there. So these are just some examples of important works why when people actually focused on that potential. I think initially in late 90s, it was, people hoped that maybe this would be a pathway to ground state molecules. I think in the end, I think it was partially done via levels in this state, but in the end, I think other approaches were chosen. So, you know, it was a very well characterized potential, so we felt like we could try and test our laser system. So, but when you start measuring, we encountered this paper where the group of Olivier Douliet claimed that in this external well, there's actually 2 vibrational levels that are missing, meaning what the people had thought was the ground state of that external well. It's actually not the ground state, but the second vibrational state. So there should be 2 more vibrational levels. The problem is that, first of all, people from Paris, they didn't see it in their experiments. Other groups, this is I think from Matthias Weidemüller's group, they also, I mean, they explicitly say that they looked below that V0 level and they couldn't find anything. So in a way, this prediction was in contradiction with what people had measured. But there was a work 6 years later where there was actually supposedly a confirmation of this theoretical work. The problem was, when we looked into that, we just wanted to really test our lasers and nothing more. When we looked into that and started reading these papers, so we got really confused because in following papers, they were like not really clear whether they believe in this result. So we were not sure either whether we should look into this or not. But we did like probably the simplest or the most obvious thing. If you have a lot of data, the blue points are from the group in Paris. So we just assume this is, let's say, an anharmonic oscillator. So we used old data and assumed that if this point here was the last one that they measured, so if this is not V0 but actually V2, then let's assume that this is an anharmonic oscillator. So these levels that we were looking for would be here. So we looked and we didn't see anything. But we also confirmed that what was reported as these new levels was actually levels that were actually quite well known, and they were here. So this along this red line. We did some spectroscopy to figure this out, and then actually it turned out that at some point it looked like we couldn't see anything. Well, it's just a laser system frequency locked to the an optical frequency comp. So that we really wanted to do it precisely, but we couldn't see these two levels. So obviously, we could probably it was sensible to assume that they are simply not there. But at the same time, I mean, should we trust the theory or not? So we did quite a bit of investigation. And first of all, these two levels, they were predicted to be, so the overlap of the wave functions was supposed to be extremely low. If you compare it to please not get confused. From now on, I will be, when I say ground state, I refer to our measurement. So this V2, this is actually what thought to be the lowest vibrational level. So the predicted by Olivier Dulier, Frank Condons were like orders of magnitude. This is 10 to the minus 3 here. So orders of magnitude lower than for the this old V0. There was supposed to be an enhancement on a Feshbach resonance, so we actually tried looking for that, and it turned out that, unfortunately, the place where we would expect this level to be is here. So there's a huge broadening due to other molecular levels, or molecular levels. So it's somehow buried here, and that's when we use this magnetic field or the Feshbach resonance at 48 Gauss. Obviously, this is something that we didn't want to use because it's fairly narrow, so that's why we started with the broad one. It turned out that actually, yeah, this was actually the answer, it seems, at least. When we used this Feshbach resonance to enhance the photostation rate, we did manage to see the predicted level. So let's call it, well, V1. We just, in case we confirm that we see V2, which used to be V0, and we did see barely, but it's exactly where it should be. We saw V0. So I guess we are fairly confident that we are able, or that we were able to detect these missing levels that were predicted by theory. And this is actually, unfortunately, a somewhat mean experiment from our point of view, because the window where we actually could see it, it's around the Feshbach resonance, and it's pretty much as wide as the Feshbach resonance for the V0 state. It's much better for the V1 state, so this was a little bit easier. But when we saw this, now obviously there was this obvious question, is there still this V0, or maybe that's only V1? So yeah, they are both there, and due to the fact that our laser system was really nicely stabilized to an optical frequency comp, we're able to, among other things, measure the AC Stark shift, and in fact, we also confirmed that the Zeeman shift was pretty much exactly like what you would expect from just the change of the energy of cesium atoms in the MF3 state of the F3 MF3 state. So really the ground state of the species. Yeah, okay. So yeah, in the end, we just measured this actually quite precisely. There's still quite a bit of work we have to do to maybe to analyze this data, but definitely the levels are there. Okay, so this would be everything. Thank you.
So thanks for the wonderful talk. Questions? We should throw this. Where's the cube? Yeah, let's just throw it somewhere. See what happens. I'll throw it. Yeah, actually, Jeremy had a question.
I have a question too.
Oh, you do have a question. Oh, wonderful. Oh, great.
Yeah.
I didn't
Actually,
know.
you already have the fiber resonance. Can you, for example, make some cesium fiber molecules and start from there to look for levels that will enhance your transition?
You mean for KCS or
No,
cesium?
that's cesium too.
And
The cesium fiber molecule seems to be very easy to make, right?
yeah, they might be, but so actually. It's a little bit annoying, unfortunately, because right now in our setup, it's probably just the densities that are not really high enough, and we can't really see Feshbach resonances in cesium in the in elastic losses. So we located the resonances, actually using the method developed by Professor Chin here by using blue detuned light. So actually, it wasn't exactly this method because we were using light that was close to one of the photostation lines. So effectively, it was I don't know, maybe it's a reversed Feshbach optimized photostation. We just used photostation to optimize Feshbach resonance detection. So we actually couldn't see the loss in that, but it was really nicely enhanced, and also this effect. So probably partially this was an issue of the density, why it was hard to see. But on top of that, so I mean, so we could have swept at that time across the Feshbach resonances, but simply we couldn't really see the Feshbach resonance using a standard method. So I guess I felt like this would be not useful for this search. And just to create Feshbach molecules of cesium, I wasn't sure, or still I'm not sure what I could do with them. I mean, there's probably a lot that could be done, but.
Yeah. So in your KCS resonance measurements,
Yeah.
I mean, first of all, what's your temperature? And secondly, do you have an explanation of what on earth is going on in the potassium 41?
So the temperature is, I would say, somewhere between 1 and 5 microkelvins. So I mean, it's probably not very cold, but also not too hot. That's one. And second, so one, I think the predictions that we based our initial search on, I might have not included P-wave Feshbach resonances. And actually, many of these are non-S-wave resonances, mainly P-wave. Well, actually, P-wave resonances. So I think this one, which is at 130, was I think predicted at something like 160 or so, and it was supposed to be 150 milligauss wide. This one is a bit wider. I think maybe this one is S-wave, and I think this one is a P-wave resonance. This one probably as well. So there were some issues with that, and Matthew Fry has actually done with Michał Tomza theoretical analysis of that. So at this point, it seems like this is all explained, but we still need to sort of converge on exactly what are the details of that.
Any further questions? I would love to throw this one more time. I don't know. Oh, great. Okay, well.
Good luck.
Ah!
Almost.
It was pathetic, yeah. Sorry.
well, for a physicist, it actually might not be
Not
that
so
bad,
bad,
right?
right.
So
It was not just 1 meter.
yeah.
So there are people who really doubt Olivier Dulieu?
Well, I mean, I didn't. I know. I actually, I didn't. That was the problem because,
Okay.
right?
Yeah,
I
no,
believe that
you're-
that's
you're-
true.
You're the good guy, right?
I guess. Well, I guess I confirmed that he was right, so it's even a better guy. maybe.
Yeah.
Well, not that he than him, but I'm just saying
Yeah.
than just good.
Very good question. Thank you. Very much. Well, then,
Okay.
if there are no more burning questions, let's think. Mariusz, one more time.
Thank you.